So the front part of this compound goes with the back part of the other one and makes this compound. The front part of this one goes with the back part of this one and makes this compound. You look up the charges in the formulas. You find that this is a plus charge and a negative charge. This is a plus charge, that's a negative charge. And you have all the references, test references, to figure that out. So then this is a 1 plus charge, it's a 1 negative charge. So this compound with just one of each of these is charge balanced. You have to write a balanced compound. In this case, it's reasonably easy in that I've given you 1 to 1, 1 positive and 1 negative. But if it's not 1 positive and 1 negative, you have to balance the compound. Okay, this happens to be 1 to 1. But if it's not 1 to 1, say silver was 2 plus, you'd have to have 2 chlorines. You have to know how to balance it. And you have to remember that subscripts like this only travel when they're part of a polyatomic ion. In this case, they're both traveling because they're both part of the polyatomic ions. You don't move subscripts over that are not part of a polyatomic ion. When you figure out the physical states, if you look on the solubility rules, you'll see that ammonium compounds are always soluble. Turns out so are nitrate compounds, almost always soluble. So this is going to be aqueous. If there's water around, these are aqueous, meaning they're dissolved in water, so there's water around. If there's water around, soluble compounds are aqueous. Silver chloride, on the other hand, is not going to be soluble. Okay? If you look on your, and I would suggest you look on your solubility rules now and see where we're getting this from so you know how to use it tomorrow. Chlorides are mostly soluble, but not when they're bonded with silver. So this is going to be a solid. So the question says we're starting with, well, we need to balance the equation. I'm going to speed it up by telling you this is already balanced. And on the test, you have to show me the atom inventory. Okay? It may be balanced, but you got to show me that it is. Got that? So what we're going to do is we're going to start with this amount of the starting amount. That's 15.5 grams. That was in the problem. And we're going to calculate mass to mass to the product we're looking for. We're looking for the solid. And then as a separate mass to mass problem, we're going to start with the 62.2 grams of silver nitrate, the other reactant, and do a mass to mass calculation to the solid. We're not going to get this number. This is the actual yield. What we're going to get is 2 different amounts of silver nitrate. And we're going to use those 2 amounts to figure out which one is the theoretical yield. So let's do the mass-to-mass calculations then, starting with this amount of ammonium chloride. Now we need to know the molar mass. Okay? So Alex, since you asked me about this, do you know how to calculate molar mass? Okay. Well, let's do that then. What we're going to do is we're going to write down all the elements in the formula vertically. This is how I teach you to do it. And put down the atomic masses for each element. So go to your periodic table and find the atomic masses. If you know how to calculate the molar mass, you should be doing this now so you can practice. If you don't know how, you should have out your periodic table at the very least and working with me because I'm trying to help somebody else understand as well. There's no excuse for you not to do this work. You got them all, Alex? what's your periodic table? You found it? Okay. Okay. You got them all written down now? All right, so what we're going to do is we're going to look at the formula, and we're going to multiply the atomic masses by the number of elements or atoms we have in the formula. So I have 1 nitrogen, 4 hydrogens, and 1 chlorine. So we're going to multiply this by 1, this by 4, and this by 1. You want to be very careful to keep all of your digits lined up the way you learned to do this back in first grade probably. Or maybe when you're doing decimal places it would have been in a later grade than first grade. But if you keep the digits all lined up, we can see that we've got empty slots in 2 different columns. And that's how we're going to figure out what our significant digits are going to be. We're to add all these together. The definition of molar mass is the sum of all the atomic masses of all the elements in a formula in units of grams. And that's equal to a mole. That's what a molar mass means. It's equal to a mole of that substance. Yep.
Are you recording?
I am. That's part of the plan. Okay. Have you added them together? Okay. Okay. You got 53? Oh, I hit a 2 instead of a 5. Thank you for telling me that. That's why it's always a good idea to do your math more than once. Yep, 53. Okay, now, the last 2 digits are the result of adding empty slots. And so we don't really know what those numbers would be. So what we're going to do is we're going to round those off because they're really not useful to us. So we're going to underline the last 2 digits. We're going to write a rounded off answer. Now this is the mass in grams of NH4Cl, and the rounded off answer is going to be the same, 53.491 grams of ammonium chloride. And the definition of molar mass, we said, is the sum of all the atomic masses of all the atoms in a formula in units of grams. And that's a mole of that substance. So we're going to say that. It's a mole of ammonium chloride. Okay? So this is the equality statement you need to be able to solve the problem, or at least this part of the problem. What we're going to do is we're going to match units and species. Okay? So up here in our starting amount, we have units of grams and species of ammonium chloride. So down here, we also want grams of ammonium chloride. So the left side of the equality statement down here matches the units and species. So that number needs to go there. So because the grams of ammonium chloride has a number, a value of 53.491, that's what we're going to put right here. Okay? The other side of the equality statement, the 1 mole of ammonium chloride, that goes on the top. And like in algebra, when you have x's and y's on the top and bottom of a fraction, you can cancel mass or grams and ammonium chloride. The next step is we're going to need to go from one species to another. What we did in this first step here was to convert from grams to moles for the starting species. Substance A, we might call it. If you're looking at the molar map, that's substance A. We converted from the mass of substance A to the moles of substance A. Now we want to find the moles of substance B. That's what we need the balanced equation for. Okay? We need our molar ratio that we get from the balanced equation. Now we need to know which is the substance we're trying to get to. And a moment ago I said it's this substance right here. This is what we're trying to get to. We're trying to find how much of this stuff we can make. Okay? Because that's what we're collecting at the end in the problem. You got to figure out what am I collecting at the end. Okay? So since I'm collecting this, I want to go from ammonium chloride to silver chloride. Alright? And I use the coefficients in front to make a molar ratio. Now in this case, all the coefficients are implied ones. That might be 3s and 4s or something. You have to use what coefficients are there. Okay? You can't just plug in a 1 because you want to. You got to use the coefficients that are there. So I'm going to put the 1 mole of ammonium chloride implied by the fact that we have no number there, like x's. If we want to write 1x, we don't write 1x, we just write x. So when we have 1 ammonium chloride, we don't put a 1 in front of it in the same way. We can show that as 1 mole of ammonium chloride on the bottom here, and whatever number of moles of the thing we're trying to find, that goes on the top. And that's 1 mole, in this case, of silver chloride. And once again, we can cancel units and species. It depends on which one we're working with. You have to know, I'm starting with this species, so that's the one we're using here. If I were starting with this species, I'd use that number there. Every step in this mass-to-mass stoichiometry, the units on the bottom here and the species on the bottom here are going to match what's on the top in the previous step.
Yeah, I know that. I was just wondering about like 1 and 2. Sometimes we get like 2.
Right, but that depends on what coefficients were in the equation to balance it. Okay? I sort of skipped a step in that I didn't write out an atom inventory here, but this is already balanced. You understand that?
I don't do it.
Ariel, you understand that?
So, like, if you get Fe and Fe3 plus, that would be like 2.
Well, it would depend on what you have to balance the formulas, and then if I balanced the equation and needed 3 of those in the front, then I'd put a 3 down here. Okay, I don't need it here. Yes.
How do you get that AG? Is it in the problem?
Yeah, here's silver,
Okay.
and the front part of this compound joins up with the back part of this one.
I know that, but I'm like, how do you? Because I don't know. I just put the NH4, NO3 in it.
You didn't put this over here?
I put that over there. I just put that in the problem. How do you know which one?
Oh, well the problem says we're collecting a solid, right?
Okay.
Well, which one of these two is a solid?
Oh,
Okay, so yesterday I think I gave you a problem where we had 2 solids, but we said we were collecting the metal. So you just have to look at what the problem says. What are we collecting and figure it out.
What if it's like in the aqueous?
Well, and you could be collecting some aqueous substance. You could do that. You just evaporate the water out of it and get the aqueous substance behind if you wanted to.
I'm still like in the problem, you could like in the aqueous. It's like all reductions in the aqueous liquid or something. So it's can we find an aqueous?
If it's asking you for the aqueous stuff, yes. Okay? You have to read what the problem says and find what the problem says to find. Okay? There's no magic way to figure it out. Okay? It's not the same every time. You have to read the problem and figure out what the problem's asking you. Okay? In this case, the problem says we're collecting the solid. Well, that's the only solid. Now, once we have moles of the other species, and that's what the molar ratio does, it allows us to go from one species to another species. Once we have moles of the other species, now we want to convert that to grams. We want to convert it into something we can measure. You can't measure moles. You have to convert it into something you can measure. So we need the molar mass of silver chloride. Okay? So we go back down here and calculate molar mass for silver chloride. If you haven't done that already, please calculate the molar mass of silver chloride. In the same way we did for ammonium chloride, calculate the molar mass of silver chloride. You're asking what its atomic mass is? It's element number 47. You found it already. I see your finger on it. Okay. Now here's something that sometimes students will get wrong. Please listen. When you're figuring out molar mass, you don't worry about any coefficients in front of the formula. With molar mass, you're only looking at the number of atoms in the formula, not the coefficients in front of the formula. Does that make sense? When you're figuring out molar mass, it's only the elements in the formula, has nothing to do with the coefficients in front. Coefficients are taken care of in the molar ratio. You don't use them again when you're calculating molar mass. We have one empty slot to the right. Now for addition and subtraction, anytime you're adding a number to some empty slot, well, that digit that results, I should say a digit, anytime you're adding a digit to some empty slot or subtracting with an empty slot, your resulting digit is going to be insignificant. We underline it and we round it off. And we have another equality statement. If you do what I ask you to do, you're going to write the molar mass, which is this number, and you're going to say that's equal to a mole of that same species. Since we're doing that every time, then you'll have the equality statements you need for the conversion units up here. Now in this case, I've got moles of silver chloride on the top. So Alex, I want you to pay attention here just a second, okay? I hate to interrupt you, but notice we got moles of silver chloride here. Therefore, we want moles of silver chloride on the bottom here. And it's the right side of the equality statement now that goes in the bottom. Okay? You can finish what you were doing. And again, we cancel units and cancel species. And we're ready to do the math. The fast way that I told you to do the math is to multiply everything across the top, hit enter or equals, then divide what's on the bottom, hit enter or equals between each thing on the bottom you're dividing by. And in this case, we've only got one thing to divide by because the ones don't really matter to us. Dividing and multiplying by 1 just gives us the same answer. Your final answer will have 3 digits. So initially, before we round off, we're going to get something with a lot of digits behind the decimal. No. Right here, you're doing addition. So you use the addition rules here.
That's what I did.
No, you didn't. You used the multiplication rules. For addition rules, you only get rid of the last 2 digits.
Oh, okay.
For addition and subtraction, you only round off those digits that are resulting from empty slots. Now, this problem here is multiplication and division. Okay? So now we're going to find the measured or calculated number with the least digits, and we're going to round off our answer to that same number of digits. Yes. 41.52 and some more digits. Is that not what you got? Well, let me check. Might want to make sure 15.5 times 143.321, enter, divided by 53.491. Getting the same answer again.
Oh, well, I got the 401.52.
Okay, did you check your math? Well, I don't know what to tell you. Are you getting this answer or a different answer? And you're putting these numbers in the way I've taught you to do it. 15.5, 143.321, hit enter, divide by 53.491.
See, this is what I have.
Well, this is the same answer.
It is?
Yeah. See, only difference you have is your calculator rounding off at this 7 here.
Oh,
Since the 9 is there, it's rounding up to an 8.
Okay, never mind.
That's okay. No. So your calculator does round off. All right. Now, again, this is multiplication division. So I'm going to look at measured and calculated numbers. I'm not going to look at the counted numbers like these ones. 1s, 2s, and 3s, and 4s. Single digits. Those are counting numbers. We're not going to use those. We're going to use only the measured number like this one, calculated numbers like this one and this one. And of those numbers, find the one that has the least number of digits. And that's this number here. It's 3 digits. So we want to round off our answer to 3 digits. 1, 2, 3, and round off all the other digits. Now, I still haven't put my units and species over here. I've got grams of silver chloride. And I'm going to round that off now to 41.5. All right, so that's one of the 2 numbers we need for mass-to-mass calculations. Now we need to go back and do the same calculation, only this time starting with 62.2 grams of silver nitrate. Splitting that over 1. We need a molar mass for silver nitrate. Silver, nitrogen, oxygen. 107.8682. Nitrogen is 14.0067. Oxygen is 15.9994. We have 1 silver, 1 nitrogen, and 3 oxygens. Did you put $1 in there? You put $1 deposit in there to use the calculator from me. Okay. I don't want your crutch. All right, so Ariel, since you were asking about this a while ago, notice there's no empty slots here. So there's no reason to round anything off here. Okay? So this is you don't need to round it off, so this is silver nitrate's mass without the need for any rounding off. And we could say that's equal to 1 mole of silver nitrate. Every time you calculate the molar mass, you're going to set that equal to a mole of that species. Well, we have what we need now for this equality statement. I want to match the units and species I have in the starting amount with what I put on the bottom. And the left side of this equality statement here, the grams of silver nitrate, match those units and species. So we want this side to go on the bottom of this fraction here. The other side of the equality statement, the right side, goes on the top. You understand where we're getting all this?
I don't get how you get the 1 mole of AgNO2.
You just have to know that's what it is. Okay, the definition of molar mass, that is to say, the definition of how you find out how much mass there is in a mole of a substance is to add up the sum of all the atomic masses of all the atoms in the formula. That's what this is. We're adding up the sum of all the atomic masses of the atoms in the formula, and you put it in units of grams. That's the definition. That's a mole of that substance. So we just write it equal to 1 mole because that's what it is. It is equal to 1 mole. Does that make sense? Okay. What we're doing is mathematically stating the definition. Okay? Huh? That's all. I want you to write it down every time because that's where we're going to get this from. And if you practice this part should be pretty easy. Okay? Huh? Well, it's already turned into a solid. What we're trying to do is calculate the amount of that solid we could possibly get. Yeah. And that's what determining theoretical yield is all about, finding the maximum amount of product that could possibly be gotten. That's what theoretical yield is. The maximum amount of product that could possibly be gotten.
So it's like the fourth one will be the same as the first one, like the fourth little...
This part right here?
Yeah.
Yeah. Yeah. Okay. So we're going to cancel grams and silver nitrate. Now we need a molar ratio that goes from silver nitrate to the thing we're looking for, silver chloride. It's still a 1-to-1 ratio because that's the coefficients we have in the equation. So I've got 1 mole of silver nitrate right here. I want to match that with the units of silver nitrate here, units and species, 1 mole of silver nitrate. And we're trying to find the solid, and there's 1 mole of that. So I'll put that on the top. And since we've already got the fraction we need to convert this into grams, well, let's cancel the units of species so you can see.
Will it be like that for all of them?
Anytime you do 2 mass-to-mass problems like this to find theoretical yield, yes. There are different ways to calculate theoretical yield. Most textbooks do it in a different way, but some of them do it this way. If you do it this way, then you'll always use that same fraction at the end. Okay? So the units and species cancel here. And we're going to do this math. Alright, so 62.2 times 143.321 . And then divide by 169.8731. Alright, got to look at all our measured and calculated numbers in the problem. Remember, counting numbers don't matter when we're figuring out significant digits. This is a measured number. There's 3 digits. This is a calculated number with 7 digits and a calculated number with 6 digits. So all of those numbers, this has the least digits. That's the number of digits we want in our final answer. So we're going to count 1, 2, 3. Those are our significant digits. We're going to underline everything else. I need units and species here. This is grams of silver chloride. I'm going to round it off. And so this is 52 point, the 7 makes the 4 round up to a 5, and that's grams of silver chloride. Yep. All right. Now we have 2 masses for the same species. 2 masses for the same species. And what this does is it helps us to figure out what our theoretical yield is. The smaller of the 2 masses will be the theoretical yield. The smaller of the 2 masses is the theoretical yield. So this right here, this is smaller than this one is. So this is the theoretical yield. Okay, because it's smaller. Okay, the smaller the 2 amounts of the product, that's the theoretical yield. The chemical that we started with to calculate the theoretical yield. Once we find this is the theoretical yield over here, the one we started with here, just the chemical species that we started with, this is the limiting reactant. Okay. The other chemical we started with, the one that didn't give us the theoretical yield, that is the excess reactant.
Which one do we use for our percentage?
Percentage yield is calculated with the actual yield and theoretical yield. Okay, so let's look at that. Has everybody got this right now? Yeah. Yeah, see this, we said that in the problem, there was 35.5 grams of some solid. Well, the only solid made was the AgCl, okay? We figured that out by using the solubility rules. So then this must be the amount of silver chloride. Okay, that's the actual yield. This number right here is the actual yield of this silver chloride. Okay? So now, the percent yield is going to start with actual yield divided by theoretical yield, and then multiply that by 100. So for percent yield, we're going to take actual yield, put it over theoretical yield, and multiply the division. That's called, what's it called? What's the answer to the division called? Quotient. The quotient here is multiplied by 100 to get the percent yield. Okay? So the actual yield here is 35.5 grams of silver chloride. 35.5 grams of silver chloride. We're going to put that over the theoretical yield. That's this amount, the smaller of these two amounts. We're going to do that division right there first, and then multiply the answer by 100 to get the percent yield. Now it's important that you note, anytime you're calculating percents, you're going to cancel out units. You need to show me that. Sometimes you cancel out the species too, and sometimes you don't. In a percent yield, you're going to cancel species because they're exactly the same. Yeah? What are you doing? Alright, again we want to round off to the correct number of digits. And we have 85.5%. Now it's not enough to tell me it's 85.5%, you need to tell me what that applies to. And that's the yield of or in AgCl. One thing that I said before is a definition, a way of thinking about what a percent is. It's the part over a whole times 100. Well, the theoretical yield is the whole. That's the whole amount that you can possibly get. Okay? The theoretical yield is the absolute maximum amount of product that you could possibly get. You can't possibly get any more than that. If you get a percent yield that's more than 100, there's something wrong. Okay? Either you have an experimental error in your lab, or you've done the math wrong, or you overlooked something in the calculation of what your theoretical yield or your actual yield is. A lot of things you can go wrong. You got to be careful about it. Okay? So in the last lab, the one we did most recently, where we collected all that yellow stuff at the end, you should already have your percent yield in that worksheet. Calculate your percent yield and put that in. Okay? Any questions about how to calculate percent yield? I've been about as detailed as I know to be here. I don't know if we have enough time to spend that much time. We only have about a half an hour left in class now. Okay? I can give you one, but well, I suspect you're only going to have time to do one. I mean, I don't think anybody's fast enough yet to do more than one in a class period. not with other things. And you also have to do some, other math too. So, All right. What? No, I didn't say that.